So first question to be answered is, okay, why should we do surface processing? I think that Julien already answered partially this question. I think there are four main reasons. The first being that there are non-fully sintered particles on the surface of the part, which means possible contamination in later process. Let's speak about, for instance, aerospace applications or medical applications. We cannot accept that some powders are released. The second reason should be, let's say, low roughness. That is not achieved using additive manufacturing, so it means that for the mechanical properties it's not that good. Another reason could be that, okay, if we want to do a surface functionalization after the production of the part, we should have a surface that is compatible with that surface treatment. So it means that there should be no oxide on the surface, which is not the case for parts produced in additive manufacturing. So it calls for surface processing, namely a material removal step, which I'm going to talk about in this presentation. And after that, once we have a part with a good finish, we can think of giving to it better surface properties, corrosion resistance properties, etc. And so it calls for a surface functionalization. This will be described later by my colleague Florine Dominica and Patrick Kozmans for the plastic parts. So today I'm going to give some results achieved at CRM about metal parts, namely in titanium, Invar and aluminum. So, okay, so as Julien described before, the parts produced in additive manufacturing have that profile, have that shape. So as you can see, there are unmelted particles that could be released later. You can see, we can imagine that the roughness profile is quite high. As shown here, we have high peaks and high valleys. So we have to do a surface treatment. So another question that should be answered is, what is the material removal to be done on that part to get to the dense area of the part? Okay, one solution could be to cut the part and to have a look at the profile, to see the height between the peaks and the valleys, and to know, okay, we should remove 200 microns or something like this. But what I propose to do is, what we have done, is to do interferometry measurement, do a mechanical grinding down to a known depth to reach that kind of profile. So it's a 3D profile, and to record that free roughness values. So it's not RA, it's surface values, so surface roughness, peaks and valleys for different grinding depth to plot that kind of profile. So we can have here those values, SP, SV, SA versus the material removal depth. So what we observe is that, okay, if we only focus on the roughness, average roughness, as Julien described before, we could think that at that point, around 150 microns, we have something that is quite good because roughness is really low. But unfortunately, if we look at the valleys, we can see that even at that point, we still have a lot of valleys. So we have a low roughness, but a significant amount of valleys. If we want to be free of those valleys and to be in the dense area of the part, we should go lower and reach that point. This was what I thought till last week, because at that time we did some tensile tests on some specimens, and we saw that even for titanium SLM in this case, if we removed that amount of material, we still have unmelted particles on the edges of the parts, which means that, okay, we have removed a lot of material, but there are still below that unmelted particles. But okay, this can give an overall idea of what should be removed for different materials. So for titanium ABM, we are around 250 microns. For aluminium SLM, we are lower, and for Invar, we have that kind of value. So Julien already introduced the different methods to be used for material removal. I will just browse them quite rapidly. So we have the sandblasting methods that can give that kind of results. It's a manual method, it's not automatic though, so we can imagine that for many parts it's not that kind of interest. Best in class process. So everybody gives that picture because, okay, it's really beautiful, but we don't know what is done on the part. So for me, the interest is quite limited, but okay. Okay, Remscheid process. Julia already talked about it. We have the laser remelting. I will give some results for tests that we have done at CRM. There are also some kind of systems like the abrasive flow machining. So the idea is to put the part or the sample in a tube, let's say, and then to push a paste in both ways to grind the surface. So it's more automatical than that kind of system. So it's automatical, and that can give good results for parts having channels. We have plasma electrolytic polishing. We have done some trials at CRM, but okay, at the moment the system is not that good. Electrochemical finishing, etc. So today, okay, I will not speak about, but there are also thermal deburring, laser ablation, etc. But today I will focus on turbo finishing, chemical polishing, electrochemical polishing, and some results about laser polishing. So, okay, it can also be interesting to have that kind of table that gives let's say, a resume of all the methods. We can see, okay, it's a quite complex table, but it's really interesting because we can see that none of the listed techniques here can have 3+ in every row, which means that, okay, some techniques can give low roughness, but have poor accessibility. Some other methods have really good accessibility, but cannot reach low roughness. Okay, some methods are really good, let's say, for safety reasons, but for other reasons, they are not that good. Or some methods are really dangerous for the compounds that are used, etc. So I think it's really interesting to have another look at all those methods because none of them can be really good at every point. Okay, I think that those slides are within the USB key, so don't take pictures. I don't think it's necessary. So I'll give just a few words to the techniques that I have used. So as I said, turbo finishing, electrochemical polishing, laser polishing. I will not talk about chemical polishing because it's quite easy, so it's not that interesting. So the turbo finishing is a mechanical chemical surface treatment. So small abrasive, like those ones, really small, they are put in movement, and they slowly abrade the surface of the part. So the removal rate depends on the size of the abrasive, the hardness, let's say, the frequency of the engine, the composition, etc., etc. And so, as Julia said, it's really efficient at removing peaks because it's only a grinding. So if you have that kind of surface profile, you reach that kind of surface state. But it's really slow, as will be shown later. Electrochemical polishing, so it's okay, electrochemical. Treatment duration are shorter than for turbo finishing. It's around 3 hours, depending on the initial state and the goal of the treatment that you want to reach. There are lots of parameters to be tuned, so duration of the treatment, current or voltage, type of solution to be used, size of the control electrode, etc. So lots of parameters, but it's quite fast. And we can see here that contrary to turbo finishing, we have higher roughness, let's say, that we reach, but we also have a kind of waviness. It's really hard to have something really smooth. So for the laser polishing, is the last slide I had it because it's the last test that we have done. It's only a remelting of the surface. So the treatment duration depends on the parameters, namely on the scan rate of the system. So there are lots of parameters to be tuned, so the overlap, the laser power, etc. And the treatment is quite fast, I think, for that kind of parts, but the accessibility is really poor. So it means that the laser has to reach the area to be treated. So in this presentation, I will give some results for those 3 materials and for those 3 methods. 4 methods, sorry. Just So let's speak about electropolishing of titanium. So these are the kinds of results that we get when we do electrochemical polishing. So we start at a roughness of around 21. And then we can see that in around 2 hours, we are around 4 micron RA. So it's a significant decrease of roughness. So this is the surface aspect that we get after the treatment. So we can see some waves, as I shown before. original state after treatment. So we can see that we have something that is more bright and shiny. And these are the profiles, so in black before the treatment and in red after the treatment. So we can see that we have something that is smoother, and we have, as I said, some waviness on the surface. Which means, so it's a little teasing, that if we do a small triple finishing after the treatment, we can have something really smooth quite fast. So, okay, when we have done the treatment, okay, we can say that's it, it's done. But we had a look at something else, which is hydrogen content. So because when we do a chemical or electrochemical treatment, we release gases, and for instance, hydrogen. So we have tested the amount of hydrogen in the original sample, so we get that treatment, that amount. And if we do electrochemical polishing, we get that higher amount of hydrogen. It has to be known that hydrogen leads to embrittlement of the part, so it has to be avoided. So we have done a study, and we have shown that after a good thermal treatment, we can be free of that peaks around 600 Celsius degree, but it has to be known. So doing only the surface treatment is not that. You have to think about the thermal treatment. So concerning triple finishing, as I said, okay, we can go to really low roughness. So starting from 22, we reach 3, 2, but it means longer treatment duration, around 30 hours. So as I said, it's a kind of grinding system. So we start from that kind of surface, and as the treatment proceeds, we can see that we are slicing, see, the surface, and we get something that is smoother. As a consequence, profile, we can see that we have something really smooth, but we have some valleys. As Julien said, it's hard to be free of those valleys through triple finishing because it means lots of material to be removed. Last week, we have done some trials about laser polishing on parts made in additive manufacturing. It's very preliminary trials, but I think it's quite interesting because we decrease roughness from 25 to 9 microns on titanium EBM. We have that kind of aspect. We have some oxidation depending on the parameters, and we have that profile. So we can see here that we observe the width of the tracks, and between each tracks we have something that is quite smooth. So I think these are really interesting for preliminary trials for laser polishing. So now let's speak about INVAR, about chemical polishing of INVAR. So samples produced in INVAR have a lower roughness, around 15 micron RA, and we can see that we achieve 3 microns on overall surface of the parts in around 1 hour. So it's really, really fast. So we have that surface and we reach that state. So the material removal is really, really fast and homogeneous. Here too, I will not put the graph, but we also have to have a look at the hydrogen because, okay, in the as-built state we have around 2 ppm. When we do the required thermal treatment for INVAR part, we go down to around 0. And after thermal treatment and chemical polishing, we take a few ppm. So it means that we also have to take into account this hydrogen release during the process. We have done also some triple finishing on INVAR. So we can see here that, okay, it's faster. We are speaking of around 2 hours treatment. We have quite acceptable roughness of 2 microns, but the parts are smooth. So it means that after the treatment on flat surface, we have something really smooth, but the supports are bended. Those lattice structures are removed. So, okay, we have to take into account that for that kind of soft material is not that good. If we go to aluminum, we have the same observation. So it means that if we do roughness measurement versus time, we can see that within a few hours we can have something really smooth, below 1 micron RA. But we also have an impact on the shape of the sample. So we propose to do another methodology, namely remove material by chemical polishing. It's like this. So as I said, we are not improving that much the roughness, but we are removing lots of materials. So we can see the profiles that before and after are the same. The shape, okay, is different, but the roughness is not that changed. And after that, we do a smooth, really smooth tribo finishing, because we have a low material removal, but we get a really good surface aspect. So using that method, we are around 1 to 2 microns, and we have a quite good conservation of the shape of the sample. Here too, the same observation. We take hydrogen during the chemical processing. Tribo finishing, as you can see, do not induce hydrogen pickup during the treatment. Electrochemical polishing on titanium has already been tested, but it's not really homogeneous. I think there are issues with the silicon content on the sample. So we can see, okay, we can reach good roughness profile in red compared to the original sample, but we can see that the homogeneity of the processing is not that good. We have some craters, etc. So, okay, it has to be studied. We are not that good for electrochemical polishing. So as I said, we have some regions where we have a silicon content enriched areas that are making some kind of masks on the surface which induce the formation of some craters. But I'll go on. Okay, we also did some trials on laser polishing of parts. So we can see here the 3 trials we have done. We have not a shiny surface, but we have something that is quite smooth compared to the reference. So we decrease roughness from 5 to around 1 to 2. So I think these are quite good results to be studied, of course, because we have not done any section of the samples. But okay, there are some results, really interesting results, I think. So to conclude, I would say that depending on the material and process that we use, up to now, on my knowledge, let's say, I don't have found a method that can be applied to all the methods. We have to use different methods for different materials. So for instance, if you are using chemical polishing, it can give results for roughness decrease for Invar, but for aluminum it's not that good. Roughness is not influenced. Electrochemical polishing works well for titanium, but not for aluminum. Turbo finishing is really good for aluminum for decrease of roughness at the last step. But for titanium, okay, it works, but it's really, really long. So I would not use that method. Okay, this afternoon or later, we will speak about surface functionalization. So I will let the other people introduce that topic. So the next step that we are going to study or being studied is the effect of those surface properties on the mechanical properties of the samples. So it's a little teasing, but we are already done almost them for those materials and those treatment methods. So I will try to prepare some publications on the topic. We have to check the surface compatibility, but okay, we'll have a few words about that later. And now the next step, because we have been working on small samples, so tensile, fatigue, etc. But now the idea is to test those methods on complex parts. So I have a project for a complex part made in titanium and stainless steel, so bigger parts. I would like to do the same for Invar parts, because with the chemical polishing I got quite good results. And now, okay, because we are doing that manually, but the idea would be to do the treatment on complex parts using robots. But I think it's the questions of the Dominica later. So I would like to thank 2 projects for the funding. The first being funded by ESA, and the other one funded by the Cornet program. And I would like, of course, to thank all my colleagues that have contributed to this study. And I would like to thank you very much for your attention. And you have questions, feel free.